welcome everyone to the SIMBa seminar. Today we have Cardona from University of Strasbourg, but previously doctoral in UPC. And he's going to talk about undecidability in dynamical systems from Turing machines to hydrodynamics. Welcome, Robert.
Thank you. So thank you all for the invitation and also for everyone who come here and is interested in what I'm going to speak about. So first, you can interrupt me whenever you want, even if it's not in English or in Catalan or whatever. And I will speak about something in a very accessible way, at least for the half an hour. I think the last 10 minutes maybe it will be a bit more technical, but I won't be giving any details of the proof or anything. I will just state some questions, try to motivate them, and see why they are interesting. And that's going to be already half an hour. So as the title says, the main topic is going to be dynamical systems. So for those who have not done, because I think it's an optativa, so it just means we're studying maps or flows. In general, I'm going to think of manifolds in geometry, but in general it could be R3 or 2 or things like that. And I'm going to be interested in properties satisfied by these dynamical systems. And I will focus in systems that appear in hydrodynamics. And we will see why Turing machines are involved in this. So first, let me write the equations I am interested in. So what I'm going to work with are the Euler equations. These equations model what is called an ideal fluid. So ideal means that it's incompressible, which means that you cannot stretch volume. So volume is preserved, incompressible, and without viscosity. So for those who have worked a bit in hydrodynamics, when there is viscosity, then it's the Navier-Stokes equation. So Euler equations is the same as Navier-Stokes with no viscosity. So these equations, let's say we are in R3. So you can write them like this. So let me explain what each thing means. So this U is the velocity. If you want something, in general, it's going to depend of time, and it's going to be a function the derivative. If you want the vectors within the its coordinate and so on. As you do. So this is the velocity of the fluid, and P is a scalar function, which is called the pressure. So it's a scalar function. So this second equation just tells you that the vector field is 1 intersecting all the time. So the divergence is 0. And the first one is if you want a continuous version of Newton's law. So what else do I want to say? If you don't have time dependence, if you assume that this term is not here, then you have what is called a stationary solution. One way to think of a stationary solution, this doesn't mean that the fluid is not moving, but what it means is that it moves all the time in the same way. So you can think of, let's say you are in R2 instead of R3. You have what is called a vector field. So you have like at each point you have an arrow that tells you in which direction the fluid is moving. So you might have, for instance, a closed orbit or something. So if it's not time dependent, it means that this is always like this. So if I pick a particle here, which can be a drop of water, then it's going to follow these arrows. And these are the orbits of the vector field. I will be mainly interested in stationary solutions. This is why I draw this picture. I will think of vector fields all the time. So if it was time dependent, then this vector field will depend on time. And then the drop will follow the arrow at time given. So the main questions that I will be interested in, so let me give some names. Yes, I forgot to say something. So when I will state some theorems, this is a joint work with Eva Miranda, who is my former PhD advisor, then Peralta-Salas and Francisco Presas. They are both in Madrid, at the So the main questions are motivated by, first, a question that was asked by Moore in 91, I think. So let me write the question, and then we will try to understand what. So the main point of my talk will be to try to explain what this question means and why it's interesting. So the question is hydrodynamics capable of universal computation? In a sense of computer science, let's say. This is the first question. And then another question that was asked more recently, and this is why we started working on this. This was asked by Einstein in 2015. He asked more or less the same, just using another language, which is, are the Euler equations Turing complete? So what I'm going to do next is try to explain what this means. So both questions are the same, let's say, except that here you're not saying only the Euler equations, that could be other slopes. But being capable of universal computation is going to be the same as being Turing complete. And being Turing complete is going to be a property of a dynamical system, not necessarily a fluid. It's much more general. Is there any question?
I have a question. When you say U times normal U, what does that mean?
Yeah, this is the material derivative. It's called. It means one. So it's just a notation. That's what it means. It's like you take U1, U2, U3, and you make a vectorial product with the gradient of U. So to say. Okay. So as you might expect, to speak about Turing completeness, we need to introduce Turing machines. We call this. We don't put a one, but it's the Euler equation. As you might know already, Turing machines are just like a theoretical model that they model what enables computers, right? So a Turing machine is given by the following information. We denote it by a T. It's given by 5 things. So Q is going to be a finite set. Going to be a finite set that we call the space of states. And then Q0 and Q half are going to be two very specific elements of Q. Q0, different ones. So if you think of Turing machine as an algorithm, Q0 is going to be the initial state, and Q half is going to be the halving state, which means that I stop computing. In particular, well, I'm not being rigorous, but so this is at least 2. And then sigma is also a finite set, and it's called the alphabet. It's also this cardinality. Now delta is going to be the most interesting element because it's going to give us the algorithm for the dynamics. So delta is going to be a function that goes from 2 times sigma to u times sigma times minus 1 to the 1. So now I will try to explain how to use this information to compute things. So the configurations of the machine. Let me know if I'm going too fast. So the configurations for pairs u, t in space time sigma to z. So to simplify, let me assume that the alphabet is 0, 1. You can always assume this. Let's say any Turing machine can be simulated by one that has an alphabet that is just 0, 1. So a configuration is given by a state, which is just an element in Q. And this, you can think of it as a tape. Or if you want a string of bits, it's going to be something like it's infinite in both sides. And then minus 1, 0, 1. This is t. And I will denote by a point that at the right I have a 0, the symbol at position 0. So the elements of the alphabet, I call them symbols. I don't know if I will use it, but and well, I might use at some point that in these configurations, although I'm saying it's in here, I can assume that all these symbols are 0 except finite dimension. Let me say that it has compact support. Let me just call it like this. It's not ultra important, but I'm going to use it next. Okay, so this is the configurations. So at a given step of my algorithm, I will have a configuration. Now let me tell you how the algorithm works. So as when you use a computer, you need to give some input. That's going to be just I have a space. The input is going to be an initial configuration, which means that the state is going to be the initial state. So I choose initial state and some string, which I'm going to denote the input. It's always the same, right? Q0 is always the same, it's fixed. Yes. So here, this is why it comes here. Yeah. So Q0 is just one element in Q that's going to be the initial state, and it's always in an input. You need to put this as a state. Yes. So here's how the algorithm works. So the first thing that you do is you set the configuration, the current configuration is the one. This is just for because it's easy to use this notation. The current configuration is going to be the initial one. Okay. Now what you do is you use delta. You compute delta. So delta. And what do you put in here? You put the current state and the symbol that is in position 0. But I denoted before by T0. So this gives me some T prime, some T theta, and some epsilon, which is -1, 0, or 1. And now the new configuration of the machine is obtained as follows. So I change the symbol that is in position 0, I change it by Euler. So the one that I was given by delta. Next we will see an example, it's much more easy to understand. And then I shift. What this means is that if I have this, let me erase it. So if this is my configuration, first I change T0 by T0. And then shift means moving left or right my sequence. So for instance, if epsilon equals +1, this is going to mean left shift. -1 dot T1. So that's going to be my new thing. And say that I obtain a tape that is going to be denoted by. Now, my new configuration is Q prime. And then if you want 5-step, if Q prime is Q5, stop. If I reach the halting state, the algorithm finishes, and this is the output. And otherwise, I go back to step 2. So, well, let me just give an example. Let's say that my initial state is this one. And Q0. And then delta Q0. 0 equal from Q1, 1, minus 1. So what I'm going to do, first I change this 0 by a 1. And then I shift to the convention right. So I get, okay. Let me have 0, 0, 1, 0. My new configuration is this state and Q1, which is the image. So that's it. You can see that this is like an algorithm. So the whole point of this Turing machine is to know, so if I'm given a Turing machine and an input, is it going to have or not? So this depends, of course, on the input. Yeah. Because, as you can imagine, it's very plausible that it's going to have or that it's never going to have. Like it could happen that for instance, yeah, let's say in this example, if Q is Q0, then you're always going to shift to the right and keep changing zeros by ones, and it's never going to finish. Right? So you can have examples where the Turing machine never else and where it comes for a given input. And what we would like, but it's not going to be possible, is to say, is it possible to answer this question in finite, say, by using an algorithm in finite time? So is it true that for anything, any input, I can decide whether it halves or not, without having to wait for infinite time, which is not possible. So the theorem, this was proved by Turing, is that this is what is called an undecidable problem. So this is called the halving problem. What it means to be undecidable is exactly that there is no algorithm that can answer this question for all Turing machines and inputs. So this, what I just defined is undecidability in the computational sense. So undecidability in the logical sense means that something, a statement is not, we cannot prove that it's true or that it's false. So this implies that there exists at least one Turing machine and one input for which you cannot prove that it halves or that it doesn't. So there is a relation between computational undecidability and logical undecidability. So now that we have defined Turing machines, let me add one more fact about Turing machines, which is that there exists what is called universal Turing machines. And a way to think of, so a universal Turing machine is one complete Turing machine that is able to simulate any other Turing machine in some sense. So one way to think about it is compilers, right? So when a compiler, in fact, can reproduce any other program because you give it as an input, the program. So this is what the way of thinking of a universal Turing machine. So the universal Turing machine as input is going to take the information of any other Turing machine, and then it's going to simulate it. Okay. So now that we know this, let me now define what it means for a dynamical system to be complete. Is there any question about Turing machines?
A small question. Which are the typical sets Q and Q0? This has any in the problem that you can be anything.
Yes, no, in fact, so for dynamical systems, because we work with numbers, sigma is going to be 0, 1 usually, and Q is going to be 1, n. But it's just a notational thing. I mean, it's just a set, so you give it some name. Okay. So now, let's say that we are by X a dynamical system. So this is very much non-precise. But it really, the definition applies very much in general. So X can be a map between manifolds. Or for those who have not done geometry or whatever, let's say surfaces, n or 2. Okay. It can also be symbolic spaces. This can be a map, and the map can have properties. It can be an homeomorphism, or it's going to depend on what you're working with. With the homeomorphism, you have a differential structure. In this case, the dynamics are discrete, but it can also be a continuous so a continuous system. For example, an ODE, a manifold. Or even, so all these are finite dimensional systems, but you can also have I'm not going to be precise about this because, well, I'm going to give one statement. So you can also have infinite dimensional dynamical systems like units. This is also a dynamical system, and it makes sense to speak about Turing completeness. Okay, now let me give you the definition. Well, there are a few definitions that are equivalent. I'm going to give the one I think it's easier to explain. So let's say it is a dynamical system. And as I'm saying, you can think of a vector because this is what I'm going to work with. A manifold so X is Turing complete. Without saying, so informally, it's going to mean that it can simulate a universal Turing machine. But let me formalize this. If, let's say, a universal Turing machine such that for any given input, there exists explicit, not formal, but okay, explicit point in my space, in my manifold, or tree, or whatever, and an open set. So that the Turing machine halves for that input. If and only if the orbit of my system to this point intersects the open set. I'm going to make some drawings to explain. Well, yeah, positive orbit. So let me first do a drawing to explain this more less formal. Does anybody have a question about the definition like this? What this means, for example, let's say that you are in the plane and I have a function that goes from the plane to the plane. Then next I'm going to try to explain how it will be possible to construct one which is very complete. Well, more or less, I give an intuition. But what the definition is telling me is that there is some universal Turing machine, you just need one, so that when you give me an input, I can find a point here, which I said has to be explicit. I mean, I'm not defining explicit formally, but okay, there's a point in my manifold and some open set, so that if I take so if I choose my point here, I can look at the iterates, the positive iterates of my function. So there's p, f of p, etc. That's what's called the orbit, or the positive orbit. So what I ask is that this orbit eventually reaches this open set, if and only if my machine has that input. So observe that this point depends on the input. So for each input, I need to find one point and one open set so that this happens.
Per més explícit és que es pugui trobar
utilitzar una Turing machine, per exemple. Però, so one way to think of explicit is, let's say, rational coordinates.
Sí, però a més ho has de poder computar.
What's the word methods? Sí. The formal definition of explicit means computable point. Yeah.
There is a mismatch between like the points of the manifold being uncountable and the states of the Turing machine being countable. How the two combine?
Yes, because So I'm just saying that for each input there exists a point. So now with the example I'm going to explain, it's going to make sense because so the key idea, let's say the first idea to construct Turing complete systems is to encode every configuration as a point in my manifold.
Right.
So you're just going to need a countable number of points. You don't need to use all the points. So exactly, let me give an example with, well, it's not going to be an example of, because there is no simple example. Let me say how one would construct, or would be able to construct a Turing complete system as a function of the Turing. So let's say I choose one universal Turing machine. There are a lot of them, and they are explicit. So Turing machine. Let me then multiply T, and I'm going to assume that sigma is 0, 1 is 1 M. As I said before, this can be a 0. And so I'm going to assign to each configuration a point in a one-to-one way. So one way to do this, let's say I have a configuration, and I can assign an integer point, for example, by taking an expansion in powers of n. So I take the x coordinate, I take q plus the sum of the elements of my data at the right side, because q is going to be like this. So then in the other coordinate, the elements of negative index. Okay. So is it clear why it's a one-to-one correspondence? Because I'm using an expansion in powers of n. And this always converges because T is of compact support. Yes.
No voy a hacer una curva de nada.
Sí. Well, I'm using 2 because it's easier to draw in the plane rather than in a line. Yes, you could use one dimension. So, for example, if I have a configuration that is like this, everything 0, 1, dot 1, 0, is equal to go to 2 plus m, comma, yes, m. Yes. So if I have, for example, I'm trying to give you examples of how I use it, but how is this correspondence? This one, we're going to go to t plus n and plus n squared. Because now I have a 1 here, which gives me an m squared here. Okay. That's only to try to motivate why this is a correspondence. So this is going to give me a countable number of points in my plane. Like this. And each of them corresponds to a configuration of my machine. Now suppose that my function sends a point to the next configuration given by the output. So here I have a point that I can denote it like this because it's a configuration. And here I have one, which is the one that I obtained by one step of my output. So let me assume that my function exactly sends this point to this one to the next step of the algorithm, and so on. And as you can imagine, this kind of seems like I'm simulating my Turing machine. So indeed, what's going to happen is that I can take a neighborhood, an open neighborhood of my points assigned with the halving state. So some of these points are going to be of the form q half whatever. I can take a little neighborhood of these points. They're going to be counter-dimensional, okay. And one here and so on. Then it's clear that if I take an input, let's say this is an input, and I iterate the function, if it ever touches this open set, it means that the machine has happened. So this will be an example of a Turing complete function.
Is the open set you fixed?
But in this case, it is. In general, it could depend on it, yes. Yes, and there are definitions of Turing complete that are a bit more complicated. For instance, you could say that you fix a part of the output. Let's say you say, given an input and some finite part of my output, does my machine have with that output? And then the open sets are a bit more complicated.
Why do we need to have open sets? And instead of just saying the evolution of the flow needs to close exactly that particular open points.
Yeah, so a priori, I mean, I'm not being very precise, but it just works better because if you're thinking of, let's say, when I'm saying that this system a priori, you cannot compute it exactly. So in principle, F could only be approximable, computable, to be precise. So this means that when I compute the image of this, it might fall near the image point.
Due to numerical error.
Well, yes, if the function is not computable exactly, yes, then it's a numerical error. And then you can, okay, that's going far and far and far, because then you can try to construct functions that are robust, that are Turing complete in a robust manner, and so on. But I mean, that's one not a very precise answer, but. So well, now that we know what it means to be Turing complete, we can understand what the questions of Moore and Tao were asking. So, for example, well, let me write the theorem. So that's going to be, in some sense, answers to the question that I was mentioning. So this one is 2020. Eva and Fran. This one is saying that there exists. All right, I forgot something. The other equations, what I wrote was in R3 with the standard metric, but the other equations make sense in any manifold with a Riemannian metric and in any dimension, in fact. Okay. This is important because in this statement, what we say is that there exists some metric in the three sphere, and well, I mean, I'm putting here the three sphere, but you could think also of the three torus, or I mean, I'm just taking a compact manifold because in R3 you could have stationary solutions that have infinite energy, so it's not physically relevant. So this is why in fluid dynamics, well, you usually work with the three torus because it's more natural, but you could put here if you want. So there exists some metric, Riemannian metric, for those who have done Riemannian geometry, and a stationary solution. So I write next because it's a vector here. That is so why is this interesting? Perhaps the fact that it's saying that you could have a computer made of water, which I don't know, it's funny. The other interesting property of these dynamical systems, which I forgot to put here, is that, of course, it follows from the undecidability of the halting problem that this problem is also undecidable. So if you have a system that is Turing complete, it's not possible to determine whether at an explicit point, the orbit of the system will intersect an explicit open set, which means that there is some complexity in the system, which is not the same as chaos. For those who know what chaos means. This is different because chaos tells you that if you take initial conditions that are very close, they might diverge very much in non-time or time. But this one is telling you that even if you know exactly the initial condition, you cannot really say something about the long-term dynamics. So let me just put two more theorems so that you know more or less what is known about this. And then in the last probably 5 minutes, I will sketch the ideas of this theorem, but this is going to be just for those who want to look into it or whatever. It's not going to be not formal, and I'm not going to give definition and so on. So the other theorems, this is where I am. So this one is stationary solution. So this is more or less, if you want, answers the question of Moore, at least for some geometry. But the question of tau, I wasn't precise when I wrote this question, was about time dependent. So in that case, the dynamical system is infinite dimension. So it's a PDE. So the answer is also yes, but you need a very high dimension. And the techniques are completely different. So there exists some Riemannian manifold. I'm going to write the dimension only because it's fine, because it's very fine. The dimension of M is of order 10 to 35. Because it is embedded theorems. Where the time-dependent other equations are the. So in this case, are Turing complete. In this case, instead of an initial point and an open set, the initial point is an initial condition for the equations. So it's a vector field. And then the open set is an open set in the space of point observing vector fields. And then the last theorem is going to be that there exists a stationary solution, which is Turing complete in R3 with the standard metric, so in the most physically relevant metric. But we lose compactness. So there exists, well, this is also Daniel. Exists a Turing complete stationary solution. Of Euler equations in R3 with the standard metric. You know, this is standard. So this is really the equations I wrote in the beginning. It does not depend on a metric. But as I was saying, the solution is not of finite energy, it has infinite energy. That's the price paid. How much time do I have? 5 minutes? -5. Okay.
We'll let you.
Yeah, no, I'm not going to explain the book. I will just give a, yeah, you know, something like a sketch. So here are some ideas of the proof. So as you might already imagine, for those who have worked in dynamical systems, this reminds very much of symbolic dynamics. And so the first step is using symbolic dynamics. Using the works of Moore himself. So symbolic dynamics, for example, a very, let's say, paradigmatic example is chaos, right? So chaos, you usually find it by finding a shift inside of my system. So the shift, now is where, okay, this is for people who know this. So the shift is exemplary, let's say, can be understood or is seen as a map of the unit square. Do something like this, using Cardona sets. So what Moore did is to construct maps that are much more general than these ones and can simulate Turing machines. So these are maps that instead of 2 blocks can have any finite number of blocks. So you can have something like this. So those are blocks of the Cantor set. Then well, you just stretch it and whatever that you want. Okay. So these are maps that are more complicated than this is called the horseshoe. So using these maps, you can construct an area preserving map of the disk. So this is an idea of the proof of disk theorem. So there exists an area preserving map of the disk that is Turing complete. An area preserving is very important because the flow is volume preserving. If you have a first return map, it's going to be area preserving. And then you use something in geometry. So you use convex geometry. So now I'm skipping a lot of time, a lot of things, to show that there exists a stationary solution. That has a cross section that is a disk where the first return map is going to be Euler. So what this means is that my flow is going to have a disk like this, transverse. And my flow is going to, every time it hits this disk, it's going to be like F. So you have a point and my flow is going to be like this. So this is P and this is double P. And then it follows that because the map is area preserving, the flow is also going to be Turing complete. Sorry, because the map is Turing complete, this is also going to be Turing complete. I'm sorry because I had no time to explain it. But okay, I just wanted to explain what it means to be Turing complete and why it does. So that's it. Thanks.
Now we have questions for that.
If you go on YouTube, there is a lot of people trying to build computers out of ridiculous things like dominoes, and I've also seen videos on using computers made out of water. And essentially, once you construct a transistor, well, it's just a matter of plugging many copies of them, like side by side. If you can find a simple mathematical model of a transistor, even probably you can do it in R2. Shouldn't that kind of be a completely different approach to showing the same result?
Maybe, I'm not sure because, I mean, could be as long as you can paste some of them together or something like this. But I wouldn't say, I don't know. Because indeed, like for instance, when you construct computers made of water, like you use mechanical things and water in it. So here it's really like to have only water in space. That's the main difference. But yeah, I can see what you say. Maybe.
It's true that the ones I've seen use kind of reservoirs, whatever they call it, where you kind of pour water and at some point it fills up and continues flowing, which is not exactly, it's not a Euler flow.
Yes. Yeah, exactly. So you have obstacles and so on.
Yeah.
So to say. here it's like a fluid there, and the way to compute is to put a drop of water that you paint and wait and see where it goes.
What happens with Navier scopes? Because here you're talking about Euler equations, and Python, if I remember correctly, that was working with Navier scopes.
Yes, I mean the motivation of Tao. Well, the question he asked for Euler, because then he said, so well, the motivation is Tao showed that, well, the big question in Navier-Stokes flows and Euler flows is whether there is existence of solutions for all time. This is the big problem. And so Tao constructed an equation which is qualitatively very close to Navier-Stokes, which he calls average Navier-Stokes. And for that one, he proved that there is no up, or that there is no existence for all time. And the way that he proved that is, according to him, some algorithmic procedure. So this is why he was like, okay, let's say that I can prove that the real Navier-Stokes equations, at least for some manifold, this is why he was asking for some manifold in some dimension. For Turing complete, perhaps I can try to adapt my proof. I feel like no. Because, well, no, I mean, I feel like no, but because he has said that this seems to be not enough after we did this work. Sí, sí.
I que també hi ha mencionat el resultat, has citat com que era més natural treballar allà. Això només per la prova que heu construït o té un significat?
El què? S3?
Sí, no, treballar al factor.
O sigui, so this result works for any free manifold. So you can choose your states. The only thing is that I'm writing the three, yes, why? Because, so why people in fluid dynamics work in the three torus? Because of this. The three torus, if you want, you can think it in R3 as a cube. 25 sides. I don't know if you, I mean, in topology, you study the torus and it's given by a square, 25 sides. So the same is true with T3. And so in this case, a solution in R3 that is periodic in every coordinate is going to induce a solution in T3. So working in the three torus is like working in R3 with periodic boundary conditions. So it's really like a compact solution because it lives in a cube. So this is why it's a natural way of speaking of finite solutions.
En el segon resultat, sí, has mencionat com que era completament diferent la manera de... Però perquè això és una dimensió tan gran, o sigui, que ja no té sentit físic o...
No. But again, it's still Euler equations in a very high dimension, but why do you have this really high dimension? It's because, so constructing time-dependent solutions to Euler equations, it's very complicated. Very complicated. I mean, that I know there are periodic and quasi-periodic solutions that are explicit and so on, but it's very, very complicated. So one way that to find, because this is done by constructing explicit solutions that are very complicated. But this is not our work. This is done by other people. What we do is to construct one which can be embedded into a Euler solution. And so the theorems here are done by embedding theorems because, well, I don't want to write more. So what we really do here is to construct a polynomial vector field in a sphere of dimension 17 that is Turing complete. Then there is a theorem by Francisco Presas that tells you that you can embed that in a quadratic polynomial vector field that has some very nice conditions. And then there is a theorem by Tao of 2017 that tells you that that can be embedded in an Euler solution in some manifold. And every time you apply one of these theorems, you multiply them the dimension by quadratically and so on. That's why you get such a high dimension. And our dimension 17 comes from the fact that there are people in computer science that were constructing Turing complete polynomial vector fields and the minimal dimension they know how to do it is 17.
O sigui, aquí el que has d'aconseguir és trobar una solució per a una P donada, perquè la P és una condició i quan escric...
Yes, I know what you mean. So in fact, what happens in that theorem?
Bueno, a tots, no?
Well, I mean, when you have a stationary solution in a compact manifold, then everything is well defined. For each point you have, the solution is defined for all time. But in PDEs, that's not true, right? But what we do, in fact, so I told you, we construct a polynomial vector field in a sphere of dimension 17. So the phase space of the PDE is the space of value preserving vector fields of my manifold. This is infinite dimension. But inside my infinite dimensional manifold, that I'm writing here with 3 coordinates, there is what we do is we construct a submanifold of finite dimension, dimension 17, and inside this, for every condition, initial condition, everything is well defined for all time. So you find what is called a finite dimensional family of solutions. And then so what you do is that the Euler equations in this invariant submanifold is like the polynomial vector field that's very complete. And this implies that the Euler equation.
Pero la P és unicidial.
La P está aquí. Es un campo, it's a vector field that is the initial condition. So if you give me the input of the Turing machine, I give you a vector field, an explicit vector field, and that's the initial condition of my PDE. And then I let my vector field evolve, and that's going to draw an orbit here, because I move on the space of vector fields. You know, it's a bit.
Però no hi ha dos condicions inicials, el camp a 0 i com es mou la pressió?
No. I mean, I know it's not obvious, but so once you fix one of them, the other follows by inverting operator.
So, if there are no more questions, let's take over again. We can do a little bit of spam now, since we are here, some of us, that in 2 weeks, the 4th of May, there will be a special session of the SIMBa seminar, which will not be a conference, a mathematical talk, but a roundtable to talk about
PhD scholarships and opportunities.
Yes, opportunities to do PhDs in Catalonia, which are the public ministerios and Veritat scholarships that you can apply to. Also, information
Discussion with people that are there.
Yeah, so people who is currently doing a PhD here and who can talk about their own experience in asking for this grant, for these scholarships, and also about the masters and the different doctoral programs, because they're different in the UAB, in the UPC, in the UB. So it will be a roundtable, and you are all invited if you are thinking on at some point doing the PhD here. It will be very interesting. So it will be at the UB.
It would be at UB, but it will be also be streamed. So
yeah, you can send questions before, I mean beforehand. If you want some questions to be asked for sure, then you can send it via formulary.
There will be a form
tomorrow in the web page of the SIMBa, and all the information on this session will be there.